much of the content. So today we're going to talk about what is called heuristic search, or sometimes called informed search. We had you watch this video of what blind search is really like. If we're trying to go from Memorial Gym to the Tennessee Supreme Court, and the space that we're searching is still a virtual space. It's not physical space, it's still virtual space, but the virtual space in this case is embedded in Google Earth, Google Maps. We're searching that space, and we're in the map. We're in the context. We're not actually looking at the map. We don't have the information from the map. We have certain operators. So if we're at Memorial Gym and we're trying to get to the Tennessee Supreme Court, imagine that we're in front of Memorial Gym. We're looking outward. And one operator we can take is to go towards 25th Avenue Garage. And if we take that operator, we come to another intersection. That operator has come with a cost. And again, we're searching virtual space. So we've not actually used that cost, but in taking that virtual operator in Google Earth, we can assess an estimate of what the actual cost would be in a real physical space. We talked about going from Memorial Gym as a search problem, where we could go down some paths, like towards 25th Avenue Garage. Some of those paths might eventually lead us to places quite distant. This is truly blind search. Until we actually make a step in virtual space, we have no idea what the cost of that step is going to be. And it is completely uninformed by where the goal is. We know how to recognize the goal. When we see the Tennessee Supreme Court, supposedly, we know that it's the Tennessee Supreme Court. We can recognize it. But some paths can take us quite distant. Other paths that we might search through a depth-first search or breadth-first search will actually lead to the goal. In this particular example, a depth-first search would be absolutely terrible to employ because there are very few goals. There are very few things that would satisfy our goal in this virtual space. In fact, there's only one thing that would satisfy our goal, assuming that we had a reasonable image recognition software. And it would be this path right here. A breadth-first search would get expensive very quickly. We talked about iterative deepening depth-first search, which might be an alternative here, which would assure that we actually found the goal within a reasonable amount of time without venturing off virtually into two distant places. But we really want a way of being informed by the goal and by any information we have about where the goal resides. So returning to the map, again, when you're actually searching virtual space here, you may not have this kind of high-level view of the map, but what you do have is you do have not just an assessment of the cost for a virtual operator that you've taken. Here's towards West End. This direction is toward 25th Avenue Garage. These steps each come with a cost that we can assess, that we hope and assume is going to be a reasonable estimate of the actual cost in physical space when we would make the move. So we have that, but in addition, in an informed or heuristic search context, we also have an estimate of how far it is from a certain state to the goal. So in this case, if we follow the operator towards West End, and we're at West End, at that West End state, there would be a heuristic estimate of how far at the West End state it was to a goal. How might that be stored is going to vary. And here it's going to be a natural heuristic we might use is simply a distance as the crow flies between a state that we're at and the goal state, or a goal state. In the case of this other operator at this state, there would also be a heuristic estimate of how far it was to a goal state. In this case, if I'm looking at this, and I have, again, this is a search in virtual space, so I don't actually walk to West End Kensington. I do a virtual search in Google Earth. If I'm at this state, the cost of applying that operator appears to be about the same as the cost of applying that operator. And it is. Those are reasonably equivalent. What differs is that the estimated cost to the goal is considerably less in this case than in this case. So depending on what informed heuristic search algorithm I might be using, my heuristic search algorithm, if in fact it's using heuristics, would probably prefer to check out this state and expand it and look at the implications of searching down through this state because it appears to be closer to the goal. Then it would prefer this one to expanding this one. Now, there are a couple factors in different heuristic search algorithms. All heuristic search algorithms are going to use the heuristic estimate of remaining distance to the goal. Some are actually going to use the estimate of the cost it takes to get to the state, various states in the search space as well. And we'll talk about this. But in physical space, if we're searching a virtual rendition of an actual physical space, as the crow flies is a very natural heuristic measure that we might use. You might remember this graph from the reading. This is a very simplified abstraction of that robot delivery problem that was given in the reading for Tuesday. And R123 is the goal in this case. We're told that we're going to assume that the robot is currently in O103. And so the task is to search this space and get to R123. Now again, we don't have the luxury of having this entire graph at our disposal and being able to look at it from 10 feet up. But we're at this state, and we can apply each of these operators. We have 4 operators in this example to apply. We don't actually know these costs until we actually take the operator. So until we go from O103 to whatever TS stands for, we don't know that we have a cost of 8 there. But having made that move, we know that was a cost of 8. We don't know that going to B3 is a cost of 4. But having made that move, we can keep that in mind, that that's a cost of 4. This is a cost of 12. Again, this is a simplified version of the robot domain. You can read about the simplifications that are made here. They assume that they're actually, this simplified example is only looking at certain nodes within the original example. It's assuming that doors are all one way, and so you'll see that there's sinks here. Once the robot gets to the mail room, the robot can't exit virtually from there. In one of the examples, example 1 in the text, it assigns, it again talks about basically as the crow flies, a straight line distances being a reasonable heuristic in problems like this. Yes?
So that's actually where my question was going. When you go back to the slide that shows the whole graph, it appears that the straight line distance would not be a good heuristic because you wouldn't get there. So
Terrible heuristic.
In that case, is there a decent heuristic, or is it just kind of you got to explore them all? Like for a case like this, what would be a good heuristic?
You know, it's in this simplified case, straight line distance may not be good. If we were to relax this problem and actually the doors were two-way and they weren't omitting all of the nodes here, straight line distance might be a better heuristic. In this particular case, you know, there may be, we have to think about what a good heuristic for this problem might be. But let's talk about that. We'll talk about it. Let's go through the example, though, that's given in the book where they just use straight line distance. And in this case, these various numbers here appear somewhat arbitrary, but they say that the heuristic distance from the mailroom to our goal is 26. And based on the other actual values here of the arcs, that seems fairly reasonable. I'm assuming that the authors sort of measured this to see that 26 was a reasonable number. The straight line distance from 0109 to the goal is given as 24. The straight line distance from 0123 to actually being in the room is 4, which happens to be the actual value there. So they've given you heuristics, and an important property of these heuristics is that, or heuristic values, is that none of these heuristic values actually overestimates the actual cost of reaching a goal. And that's something that's important. You might remember the word admissibility in the reading. If a heuristic, and the heuristic is this entire function. This is the entire function that assigns locations to actual values. If the estimates from each of the possible states never overestimate the distance to a goal, then that heuristic is said to be admissible. And so we can look here and we can verify that these various straight line distances are in fact never overestimating. So in this case, we have an estimate which is exactly the actual distance, not an overestimate, a perfect estimate. By convention, and it's by common sense convention, the heuristic of a goal state itself is 0. There is 0 remaining work from going from a goal state to a goal state. So this is the goal state in this case. The heuristic estimate is 0. This heuristic estimate for H109, this shows 2 arcs, length 16 and 9 and 4. 24, which was given as the heuristic distance, presumably the length of that, scaled appropriately, is certainly less than the actual cost of getting to a goal from 0109. Yes?
So with, straight line distance, I can understand why that is admissible. When it comes to other properties, and you create a heuristic over some other dimension of the problem, how do you guarantee that?
How do you guarantee it?
Yeah.
I mean, we'll talk about an example other than physical distance in a second. And so we'll return to that question in the case of our scheduler. And as you're thinking about this, for the course scheduler, think about what a heuristic function that was admissible would look like. And then we'll talk about it. So this never overestimates. In the case of this, it's by convention the cost of getting from the mailroom in this case, because this is a sink, is presumably infinity. And we'll just say that 26 is less than or equal to infinity. I don't know if that offends any of the number theorists in the class, but that's what our program would assume. And so this is a case where clearly if our heuristic search algorithm was thinking it was 26, but in fact there was actually no way of getting out of this state, it would certainly be misleading. So in this case, it might be misled, but it would not be simply having a heuristic that is not informative, terribly informative, is not going to stop the search. It's just going to revert to something which, in the worst case, would look uninformed. the heuristic isn't meaningful, if the heuristic is nonsensical, you're basically it's not going to kill the algorithm. It's going to degenerate into something like informed search. You might remember I had a relaxed version of this robot problem in which we can also use this returning to the original map and not making the same simplifications as the text. We can also use this version. So if in the case of 103, in our searching our virtual space, one option is to, one successor would be 0101. We can move from 0103 to 0101. Again, remember, this is not happening in physical space. This is happening in a virtual search. The candidate is going from 0103, outside 103, to inside room 103. Another option is to go to outside room 105 and go through this inside room B and go through door B3. So these are 4 candidate operations that the search algorithm might try. Each of them is going to be associated with the heuristic value. These three locations are actually mentioned in the abstracted graph, but the heuristic value given for B3 is going to be 17. It's rarely the case that you'll actually have a situation where there are explicit heuristic values attached to the states. Typically, you'll have a function that generates a heuristic value. You'll have a heuristic function that can be applied to any state. So this example we've been going through of actually having heuristic values explicitly assigned to each state is going to be quite artificial. Typically, you'll have some way of computing them.